Okay, in the previously numerical example, we can see that the uncompensated buck converter has its phase margin to be really low, like below 5 degree, and the crossover frequency is also low, like 1.8 kilohertz. And also we are encountering very low frequency gain, right? So this means that we need to use a compensator to compensate those behaviors. So now let's try to see that how can we properly design this compensator to achieve a better control performance. So as I just mentioned previously, the numerical example, right, for uncompensated buck, we have the crossover frequency as 1.8 kilohertz and phase margin smaller than 5 degree. So now we want to improve, right? Improve. The target we set is that we want to achieve a higher FC to be 5 kilohertz. And also we want to improve the phase margin from below 5 degree to 45 degree. So those are the goals we set here, right? And now let's look at the uncompensated loop gain at this frequency, right? For TU uncompensated loop gain at this specific target crossover frequency, 5 kilohertz. We would observe that at this frequency, TOS has a phase change equals to minus 180 degree. And its magnitude at 5 kilohertz equals to minus 20.6 dB. Okay, so now let's do the operation to the uncompensated system to have better performance. So there are multiple steps. First step, step 1, we can introduce the PD compensator because we want to improve FC and omega M. We previously learned that PD is capable of doing this. So PD compensator has its transfer function. So C, right, S equals to GC0, DC bias times a 1 plus S over omega Z, 0, right, and a high frequency pole, S over omega P. So based on the target we set it here, so we can select the 0 and the pole frequency. So first, the 0 frequency, FZ. Right, FZ, we have analyzed FZ equals to the target FC. So probably it's better that I mark this as uncompensated, right? Uncompensated. So you won't have confusions. So this FC is the target FC times square root 1 minus sinusoidal target. Right, this is target theta. 1 plus sine theta. So after inserting the values 5K and 55 degree to here, so we can solve this as 1.7 kilohertz. And next is the pole frequency, the high frequency pole frequency equals to Fc times square root 1 plus sinusoidal theta over 1 plus sinusoidal 1 minus. Again, we're inserting the values to this formula. This will be equals to 14.5 kilohertz. Then we care about the DC gain, right? Low frequency gain. Because we want to achieve unity gain at the crossover frequency, 5 kHz, right? Based on this relationship, we can easily calculate the GC0. So that the GC0 times square root Fp over Fz should be equal to plus 20.6 dB, so that at this frequency we can achieve unity gain, right? So this equals to 20.6. Converting dB to absolute value, this equals to 10.7. Based on this relationship, we can derive the DC gain for GC0 equals to 3.7 or equals to 11.3 dB. So that the DC gain is solved. Okay, next, let's write the compensated transfer function, right? Transfer function for the loop, right? So basically, compensated TS equals to the uncompensated DC bias TU0 times the PD compensator transfer function, right? GC0 1 plus S over omega Z 1 plus S over omega P times the quadratic pole response 1 plus S over Q0 omega 0. So this part is the PD compensator part, right? Multiplying them together is the compensated loop gain. So we can first plot the body plot for this compensated loop gain. So in frequency domain, so here is the loop gain transfer function. The magnitude, right? So basically you will see that initially is the flat value. Flat value, so let's denote the dimension here, 0, 20 dB, 40 dB. So initially, we can solve the DC bias at a low frequency. So this is T0 equals to 8.6 and equals to, in dB dimension, 18.7 dB. And we have a quadratic pole, right, at F0. So there will be a bump remember the bump equals to the Q0. Bump height is 18.5 dB, which we previously derived. And then we encounter the zero frequency here. The zero frequency will incur a slow change. Originally it should minus 40 dB, but due to this zero, this will be like minus 20 dB, right? Then it hit the crossover point, FC. And then at high frequency, we have this FP, high frequency pole. This incur another minus 20 dB per decade. So here is minus 40 dB per decade. And we can also plot the phase plot correspondingly. So here is the phase angle for the loop gain, compensated loop gain, right? So we extend those key frequencies, the F0, Fz, Fc, Fp. So the phase plot will be, or again we mark, here is minus 90 degree, minus 180 degree. So initially it's flat, there's no phase change. Starting from Fz over 10, right? 1/10 of Fz, there will be slightly rise. And then it's kind of the quadratic pole response, right? Sudden drop. Then here we will have Fp over 10. So the high frequency pole began to take effect starting from the 1/10 of this frequency. So this will incur another change. So this will be flat. So beyond this point, it begins to drop again. Okay. So here is the level of minus 180 degree. So the key thing here is that we can see if you extend the crossover frequency to the phase plot, you can see that the phase margin is obviously improved, right? So we kind of designed our phase margin of phi m equals to 48 degree. And another thing is about the 1 over 1 plus t transfer function body plot, right? We also care about the 1 over 1 plus t. This is mainly because 1 over 1 plus t suppress the input variations and also output load variations. So 1 over 1 plus t can be easily plotted based on the body plot of t, right? So for low frequency range, we consider t is much bigger than 1, then 1 over 1 plus t will just be the measure of t over the x-axis, right? And here, right, same, right? Because the bump is still high, we consider t is much bigger than 1, so it's like the measure bump. Right? So below crossover point, we always consider its measure. But if the frequency is high enough, right? High enough, then the t will be lower than 0 dB. We can no longer assume that t is much bigger than 1. Actually, 1 will be much bigger than t, right? So for high frequency range, we approximate this to be equal to 1. Right? So the body plot will be like this. So what does this mean, right? This white curve means that how will the closed loop control suppress or decay the external disturbance from the line input and from the load variation, right? So this means that at low frequency range, the variations can be decayed by such a level, right? Such a level. This is like 1 over T0 equals to like minus 18.7 dB. So this equals to 0.2. The disturbance will be decayed by 1/5, right? But still, this is not enough, right? It's not that good. Although it's better, but not that good enough. So this means that the low frequency gain of 1 over 1 plus T can be further improved, right? So that we can better resist the change of the line input and the load current variation. Okay, now let's erase the blackboard. Okay, we have learned the PD compensation can improve the phase margin and also push the crossover frequency to higher frequency. But the low frequency gain still has space to be improved. So how can we do it? So we can use the PI compensator to achieve this target. So now let's see how PI can play its role in improving the dynamic response. So step 2. So we introduce the PI compensator. So combined with PD, right, we can write the combined transfer function for the compensator, DCS. So first we put the DC gain, right, and then the PD part with a 0 and a high frequency pole. So that's the originally we have just learned a PD part. Introducing PI means that we add one inverted 0 to this PD. Then it becomes PID. So 1 plus omega L over S. So this is inverted 0 and also corresponds to PI compensator. Because we introduce PI mainly to improve the low frequency gain, right? So we want to keep the 0 and the pole less affected by this inverted 0, right? So it's better that the 0 and the pole unchanged. Then we also want to ensure that the phase margin is unchanged. So usually omega L should be a rather low frequency. And if we set FL to be 1/10 of the original crossover frequency after PD compensation, then it means that the phase margin won't be changed. Unchanged. When F equals to FC, F bigger than FC. And also we set the GCM, the DC bias GCM, to be equal to GC0. If we set this to be true, then it means that the loop gain will be unchanged at high frequency. Loop gain unchanged. So those description means that the PI is mainly in charge of boosting the low frequency gain of the loop transfer function. So actually, we can plot the PID compensated loop gain body plot. Right? So here we only, because we care about the magnitude, so here I only plot the magnitude plot. In frequency domain F and 0, right? This is the magnitude (20 dB, 40 dB, 60 dB). So after we locating those 4 critical frequencies, we can plot the magnitude plot. Initially, due to the inverted 0, we will have a initial minus 20 dB per decade, right? So it will be dropping from a high level to a until it hit the inverted 0 frequency omega L, right? Then it should be flat, right? But we are approaching to the quadratic pole, so the quadratic pole will contribute a bump, right? The bump height is Q0 in dB, and then we are approaching to the 0 frequency here. So this 0 frequency serves to slightly rise the slope to be minus 20 dB per decade. And until it hit the high frequency pole, right? So high frequency pole contribute. So this is minus 20 dB per decade. And beyond high frequency pole, it increased to be minus 40 dB per decade. So that's the magnitude plot of the PID compensated loop gain, right? And similarly, we can also make up the 1 over 1 plus t magnitude plot. As I mentioned that, so here is the crossover frequency. So below crossover frequency, this is pretty high. So we consider t is much bigger than 1. So 1 over 1 plus t will be roughly equal to 1 over t. So it's just the mirror of the t, right? Okay, like this. And beyond this FC, the t will be really small, much smaller than 1. So this will be approximately equal to unity, which will be 0 dB. So we can see that the 1 over 1 plus t has much lower negative value, right? So actually, if we consider the 100 hertz, 100 hertz usually is twice the grid frequency, right? So this typically corresponds to the line input disturbance. So for this value, if we check the 1 over 1 plus t, we will see that 1 over 1 plus t equals to minus 32.7 dB 100 Hertz. This means the decaying of the line input disturbance is much improved in comparison with previously only PD compensation network. Okay, next, let's look at the line to output transfer function. GVG. So as we previously derived, GVG equals to D times 1 over 1 plus Q0, omega 0, S over omega 0 squared. So for the loop gain, right? For loop gain, TS will be equal to compensator gain times the uncompensated loop gain. So we can insert those GC of PID to here and also write the expression correspondingly. So this will be GCM times 1 plus S over omega Z, right, times 1 plus omega L over S, which is the inverted zero part, divided by 1 plus S over omega P, times this quadratic pole response, right? So where this block equals to 1 over 1 plus okay, based on the loop gain transfer function, we can approximately calculate the GVG over 1 plus T. So we can derive that this can be approximately equal to D over G TU0 times 1 over 1 plus omega L over S times 1 plus S over omega Z times 1 plus S over omega C. So this approximation is based on, so for frequency lower than crossover frequency, the 1 over 1 plus T is approximately equal to 1 over T, right? So the quadratic pole parts, the second order parts, in the denominator and the numerator, they can be cancelled, right? And for frequency higher than crossover frequency, it's like we introduce a additional pole at the crossover frequency. So we have a 1 plus S over omega C term for this approximated expression, right? GVG S over 1 plus T. Okay, now let's plot the body plot for this GVG over 1 plus T. So before we plot the suppressed GVG, let's first plot the original GVG, right? The uncompensated GVG. So here is the magnitude plot. So the original GVG, right, is just a quadratic pole response, but D is really small. D is like below than 1, right? So in decibel, it should be a negative value. So here is the GVG 0 equals to duty cycle, right? Slightly below 0 dB. And at the F0, we have a quadratic pole response, then drops by minus 40 dB per decade. So that's the originally uncompensated, right? Compensated GVG. And after compensation, so we can plot the closed loop, right? Closed loop GVG over 1 plus t. So at low frequency, t is really large, right? T is really large here, right? This is t. T is really large, so the 1 plus t equals to t, right? So we will have such a behavior. So minus 20, minus 40. And according to those approximated expression, we can plot them one by one, right? So here is the FL, and here is the FZ, and here is the high frequency pole. So it's going to be like this. So here is FC, okay. And beyond this FC, right? So it will be overlap with original GVG. So this means that for the line input disturbances, we can effectively degrade or decay the line input disturbances. As you can see, the closed loop will enable suppression of 1 over 1 plus t. And because t is really large at low frequency, so the line input disturbance will be suppressed. Okay. So in this section, we have showed the complete design flowchart for the PID compensator. So we know that PID compensator can improve the phase margin, and meanwhile can also improve the low frequency gain and to suppress the low frequency disturbance from the input and also the load current. So therefore, PID is the mostly commonly used compensator solution in our practical use. So I hope that you can study it carefully to fully learn how to optimally design the PID compensator through this class.